So we've defined the angular position, or the change in angular position, as the angle that is swept out in a certain amount of time. So for one full rotation, this point goes through 2 pi radians. So one rotation implies a change in the angular position equals to 2 pi radians. Now, I want to get an idea of how quickly this disk is rotating. So, analogous to speed, where we had it's the distance traveled, or the velocity where we had it's a change in position divided by the time taken. We are now going to define something called the angular speed, just as the rate at which this angle changes. So if a rate of angle gets swept out in a smaller amount of time, we get a fairly quick rotation. If we've got a small angle swept out in a large amount of time, we have a slow rotation. So this means the rate at which this disk rotated is 2 pi radians in 3 seconds. So we can write this as 2 over 3 pi, and the units we're going to use is radians per second. And we call this quantity our average angular speed. And we're going to use the Greek symbol omega to denote the average angular speed, and that is just the change in angular position divided by the time it takes to change the angular position by that much. So it's fairly simple to see this. If I rotate this wheel very quickly, so like that, so that was in a kind of something like half a second, I did one full rotation. I can rotate it very slowly, so in about 5 seconds we go through one rotation. So we change the position of this disk every time by 2 pi radians. It means we go through a full rotation. If I change that, if I go through that change in angular position in a small amount of time, it means this thing must be rotating fairly fast. It sweeps out a pretty large angle for every unit of time. If it sweeps out a smaller angle in the same amount of time, it's rotating slower. So this is different from speed when we had translational motion. Where we started so many meters from a point of reference, we traveled a certain distance, we ended up another amount of meters from a point of reference, and we could use that to calculate both the velocity and the speed. Here we start out with a rigid object in a certain position. It now rotates. So as it rotates, any point on this object rotates through a certain angle. That angle divided by the time it takes to rotate through that angle gives me the angular speed, and that is a measure then of how fast this is rotating. Now, let's say, as we had here, for that point on the start, we had that its average angular speed was 2 over 3 pi radians per second. And let's say that point was, let's say, 0.03 meters from the center, so the point of rotation. What would be the speed of that point that is so far from the center? So we now want to move back to, we know it has to cover a certain distance in a certain amount of time. So V is always equals to the distance traveled divided by the time taken. For full rotation, the distance traveled is just the circumference. So it's 2 pi times the radius divided by the time taken, which in this case was 3 seconds. This just is 2 over 3 pi times r. Now 2 over 3 pi we found was just the angular speed to begin with. So we can calculate the straight or the regular speed of any point on that disk if we know its angular, or the angular speed of the disk, and we multiply by how far away we are from the center of rotation, we get the regular speed. That's another reason why we use radians, because it allows for the simple conversion between regular straight line quantities and angular quantities if we just multiply by the radius at the right point. So if we use degrees, we would have gotten something like it's 360 degrees in 3 seconds. So that would be 120 degrees per second. It's difficult to move from 120 degrees per second to how many meters per second the point on the circumference travels. So using radians just makes these types of calculations a lot easier. Now this is not the end of the story. We can have, like we had with straight line motion, we can say, well, we can define an instantaneous angular speed if we take the limit where delta t goes to 0 of this ratio. So it's just instead of looking at over a whole time interval, we look at the motion over a time interval that's as small as it can be without being 0, and we look at the tiny angle swept out during that tiny interval. If we can calculate that, we know the instantaneous angular speed of this disk, and we already know if we take the limits of something like this to t equals 0, we can just write this as the derivative of the angular position with respect to time. Also, we can have that this disk rotates faster and faster and faster. So its angular speed increases with time. So we can define an angular acceleration in the same way we did for straight line acceleration. We know this must be equals to the change in angular speed divided by change in time, and we call this quantity alpha. It's just a Greek symbol again, and this is an average acceleration. And then we can get an instantaneous angular acceleration exactly the same way as before. This will be the limit where time goes to 0 of the above, and this is then just equals to the derivative of the angular speed with respect to time. So this has got units of radians per second. This will have units of radians per second squared. Right, so this is now the language we're going to use to describe rotations. We're going to think about angular positions, we're going to think about angular speeds, we're going to think about angular accelerations. Okay, let's go.